Hello, my name is David Rogala, and my partner is Sarah Aldura. This is the software-defined FM radio project for the University of Michigan Dearborn Electrical Engineering Department. Our advisors are Dr. Miller, Professor Stefka, and Dr. Awad. The software-defined radio concept is essentially a radio that is demodulated on computer hardware as opposed to traditional analog hardware. You see here we have a basic flow diagram. You'd simply take the input, perform a low-pass filter on it, convert it to a digital signal using a A-to-D converter. You perform your DSP processing, which is where the demodulation is actually done, and then you convert it to output. So what's the big deal with software-defined FM radio? Well, the software-defined radio has a number of benefits over traditional analog radio technology. It's less sensitive to component drift, which means your capacitors changing value over time and such. It's upgradable through software, which means potentially one set of hardware can demodulate many different types of signals with a simple software upgrade, and it's you have the ability to perform better demodulation since you can actually use mathematical functions inside a DSP instead of analog approximations that you would with traditional radio. Now, with our specific project, we decided to demodulate FM radio since there doesn't seem to be an abundance of FM software radios out there. And the specific choice we took is to use the indirect sampled version as opposed to the direct sampled, because with the direct sampled, bandwidth really becomes an issue and you need much more expensive hardware, especially in the FM frequency range of 100 megahertz or so. So this is a basic diagram of how our project works. We have a radio frequency input, and that passes along to something called a quadrant demodulator. The quadrant demodulator samples the radio frequency input mixed with a digital programmable oscillator, and the idea is that if you set the digital oscillator at the frequency of your carrier frequency, it shifts the frequency spectrum to back down to baseband, so that you don't need a very high speed A to D to capture the signal you're looking to capture. From there, a low pass filter is applied, and our PIC32 is supposed to be doing the sampling and sending it to a computational device like a PC or an Android. Unfortunately, we had some issues with USB where we end up having to use a sound card on a PC to do the sampling. The main idea behind our project that makes it unique is the use of indirect sampling, as I've already said. And here we have a diagram of what indirect sampling looks like. Like I said, when you mix a frequency such as a carrier frequency with your modulated signal, according to Fourier analysis, you get the difference of the two signals in the sum. So if you if you apply a low pass filter, then basically you can shift the frequency down to your baseband. And the main benefit of this technique is that it greatly reduces the complexity of the hardware that you need to perform demodulation, because the bandwidth is nowhere near as large with as it is with direct sampling. So with our project, we use pretty standard equipment for the most part. We used a standard car antenna that was picked up from Best Buy to actually pick up the signal. We used the linear LM5517 quadrant demodulator. Is probably what I'd say is the heart of the RF end, because this actually does the frequency mixing and it does the I and Q sampling, which basically the Q channel is 90 degrees out of phase of the I sampling, and that helps kill a lot of distortion that you'd have if you only had one mixer. The Silicon Labs 570 is an awfully important part as well. With this device, you write a I2C code to the IC, and it just outputs the frequency that you desire. It's fairly accurate, and it's a pretty amazing piece of equipment. Now we also have the fourth order analog low pass filter. That's to prevent anti-aliasing. We decided to go with a PIC32 microcontroller because it had the powerful features of USB, a 1.1 megasample A to D converter. And originally our idea was we wanted to use a Android tablet to do the demodulation, but once again, unfortunately, that didn't work out. Instead, we used a PC and MATLAB to perform that. For software, your PIC32 operates, you use embedded C just like any other PIC. We in particular use micro C because the libraries for I2C and USB were supposed to be pretty good, but the USB didn't pan out. MATLAB's been very important because it's allowed us to test demodulation, and that's actually Simulink is what we use to perform the real-time demodulation in the demonstration. We've used LT Spice to do basic circuit simulation. That's just simply because we don't have a copy of PSIM. And we only got so far into Eclipse and Java because the Android device we had was a version too short, and unfortunately that didn't pan out. Now, in the schematic when we designed it, there was a couple tricks that we had to do to get everything to work correctly. We basically had to use a differential amplification stage with op amps because the output of the LT5517 is differential, and that's right before the low pass filter. In order to adjust the signal reception level, we used a dual potentiometer that basically moves the maximum and minimum A to D input values, so that way we could make the best use of the 10-bit sampling on the PIC32's A to D, because that 10 bits isn't the highest dynamic range. We also had to create an artificial ground for the 3.3 volt rail. That's not a very big deal. It's just two 4.7 kilo ohm capacitors in series between 3.5 volts or 3.3 volts and ground. Then you have two capacitors in series too, and it basically for an audio signal it creates an artificial ground in between the two. The conclusion is we were able to get the project to work. Unfortunately, not quite in the way that we had initially intended for it. But the software demodulation of FM radio does work very well. You can select any station you want through the rotary encoder that we had, and the indirect sampling is a pretty powerful feature. I think it's going to become more important as software radio becomes bigger, especially with communication and computer grade devices that are operating in the gigahertz range. And Android would be nice, but like I said, unfortunately we didn't really get to touch on that much. Instead, MATLAB was our tool of choice. Thank you, and that's all.